Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will be a visual one, not through your eyes, but through the far-seeing instruments that watch the universe in silence, the great telescopes of NASA and the European Space Agency, Hubble, Webb, Gaia. They drift in space like patient eyes open to eternity, capturing the glow of stars, the shadows of galaxies, and the cool breath of nebulae across billions of years. But before we leave Earth and begin this long drift outward, let's take a moment to get comfortable. If you'd like, dim the lights, wrap yourself in something soft, let the day fall away like dust from an old map, and allow the vastness of space to become not a fearsome thing, but a quiet companion. And while you settle in, I'd be grateful if you gave this video a like and subscribed, only if these sleepy explorations bring you peace. And when you're ready, let me know in the comments where in the world you're listening from, and what time it is for you right now. It's always a small shared wonder, this thread across time zones, connecting night owls, dreamers and quiet minds. Now, onward. Let's begin not with what we see, but with how we see. Not with stars themselves, but with the light they give off, and the strange, delicate way that light becomes an image. You've likely seen the photographs. Vast pink nebulae swirling like painted silk, pinwheels of stars captured in spiral galaxies, the strange bluish shimmer of a gas giant half in shadow. But the colours in these images often don't come from light our eyes could detect. They are translations, visual metaphors. The universe, it turns out, speaks in many kinds of light, and we, clever creatures that we are, have built machines to listen. Light comes in waves, and those waves span a spectrum far wider than the slice we call visible. There's infrared light, warm, gentle, emitted by cool stars and cold dust. There's ultraviolet, sharp and bright, often born in hot places where stars are born or dying. There's X-ray light from the mouths of black holes, and radio waves from distant galaxies spinning in silence. To truly see space, astronomers combine these wavelengths, stacking and colouring them so we can glimpse what our naked eyes never could. That's why the Hubble and James Webb images feel so dreamlike. They are not lies, but revelations. And even time behaves differently through these lenses. When we look at a nearby planet, we see it as it was seconds ago. But when we look at a distant galaxy, we are peering millions or billions of years into the past. That spiral of stars, it may no longer exist. Its light simply hasn't finished its long journey across the black. Our cameras in orbit are not just looking far, they are looking back. They are watching history in motion, frozen by distance, carried by light. The Hubble Space Telescope, launched in 1990, has spent over 30 years orbiting Earth, capturing views unblurred by our atmosphere. Its images of the Eagle Nebula, the Pillars of Creation, and the Hubble Ultra Deep Field have become almost mythic, icons of space's grandeur. The James Webb Space Telescope, with its shimmering golden mirrors, now peers deeper still, using infrared vision to look where Hubble could not. Webb sees through dust into the hearts of star-forming regions, and backward toward the earliest galaxies, glowing faintly in the dawn of time. But these telescopes do not look through windows like ours. They don't capture photographs with a single snap. Instead, they gather light over hours or days, sometimes weeks, layering signal on signal, until a whisper becomes a song. They record not colours, but data, counts of photons, information about heat and energy and wavelength. Then, down on Earth, astronomers translate that data into something we can understand. An image, a feeling, a sense of presence. Every photo of a nebula, every detailed frame of Saturn's rings or a distant cluster, is the result of patient listening. A harmony between cold machinery and human curiosity, a collaboration between stars, light, time, and mind. And perhaps that's where our journey truly begins. Not with rockets or planets or vast clouds of dust, but with the quiet knowledge that even in the cold vacuum of space something beautiful is always arriving. A beam of light, a ripple in darkness, a signal that says, I was here, I shone, and now I've reached you. So tonight, we'll let those beams of light guide us, from the familiar comfort of our solar system to the far reaches of the observable universe, from the surface of the moon to the echo of the Big Bang. Along the way, we'll visit planets with rings and storms, clouds where stars are born, galaxies colliding in slow dances, and far-off worlds circling alien suns. And when it's time, we'll come home again, back to Earth, back to the pale blue dot, quietly floating in all this darkness and light. But we'll go slowly, gently, one image at a time. If you could float just far enough above the Earth to see its entire curve at once, you might notice how delicate it seems. Wrapped in a thin film of atmosphere spinning quietly in the dark, Earth doesn't look powerful or invincible. It looks precious, fragile, like a blue marble resting on an invisible thread. And that's exactly how astronauts described it. In 1972, the crew of Apollo 17 turned their camera back toward home and captured one of the most iconic photographs in human history, the blue marble. It showed Earth suspended in blackness, glowing with swirls of white cloud, the soft browns of desert, and the deep blue of the oceans. There were no borders, no cities, no wars, just a floating sphere of life. For many, that image changed everything. It offered a kind of quiet perspective, a realization that the entire story of humanity was happening on a single, shared speck. But perhaps even more profound was the moment, 4 years earlier, when a different Apollo mission, Apollo 8, orbited the moon and caught sight of something unexpected rising over the grey horizon. Not the sun, not a star, but Earth, Earthrise. A crescent of blue and white slowly lifting into the black, seen from a place where no life stirred. That photo too made history, because in that moment we became small in the best possible way. The moon has always been with us, though we rarely think of it as part of Earth's story. And yet it is. It's thought to have formed from a collision long ago, when a Mars-sized object struck the early Earth, casting molten debris into orbit. That debris coalesced, cooled, and became our moon. Since then, it has orbited us faithfully, its gravity tugging on oceans and giving rise to the tides. It slows our planet's spin, stabilizes its tilt, and offers a dependable rhythm to life cycles, waxing and waning with quiet precision. Look at the moon through binoculars, and you'll see the scars of its long life. Craters upon craters, mountain ranges and dark plains once mistaken for seas. There is no air, no weather, and no erosion. What formed hundreds of millions of years ago still remains, as if time itself decided to pass lightly. It's this stillness that gives the moon its eerie beauty, a kind of timeless hush. Unlike Earth, the moon doesn't change much, but in that very stillness it acts like a mirror, sometimes literally. During a solar eclipse, the moon passes directly between us and the sun, casting a shadow that briefly darkens a small patch of Earth. For a few minutes the day turns dim and strange. The birds go quiet, the temperature drops, and then the sun returns as if waking from a nap. These eclipses are only possible because the sun is about 400 times farther away from Earth than the moon, and also about 400 times larger. A strange and perfect coincidence, allowing the moon to cover the sun almost exactly. There's something poetic in that, isn't there, that our little satellite born from a violent collision can slip so precisely into position as to block out the brightest object in the sky. For a moment, the shadow becomes more powerful than the light. And in that fleeting darkness, we are reminded of scale, of distance, and of our place beneath the sky. From Earth, we always see the same face of the moon. It rotates once for every orbit around us, a phenomenon called tidal locking. So the far side, often misnamed the dark side, remained unseen until spacecraft revealed it. It's not dark, just hidden. And that too feels like a metaphor, that even familiar companions have sides we never see, unless we change our perspective. For ancient humans, the moon was more than a satellite. It was a calendar, a mystery, a god, a goddess. It marked time with its phases and pulled stories into the sky. Farmers watched it. Poets adored it. Wolves howled, or so the stories said. And though we've walked upon its surface, brought back rocks, left footprints and flags, the moon somehow remains unknowable. It is both distant and deeply close. Earth, too, carries that duality. From the surface we see sky and stars. We look up at the moon, but from space Earth becomes the star, the place every astronaut longs to return to. No other world in our solar system glows quite like it. The colours of life, greens of forests, blues of oceans, whites of cloud, are a kind of miracle. Earth reflects light differently. It holds it with softness. It bends it through rain into colour. It whispers, "You are home." And so, before we wander out to Mars or dive into the storms of Jupiter, let us linger here for a moment longer, on this planet where every breath you've ever taken was drawn, where every laugh, every story, every dream has unfolded, and on this moon that watched silently through it all, keeping time in shadows. They are not just worlds, they are companions in the night sky, a home and its quiet echo. Leaving Earth and its gentle companion behind, we drift now toward the sunlit stonework of the inner solar system, a trio of worlds that lie closest to the Sun. Mercury, Venus and Mars, three neighbours sharing the same celestial street, yet each wrapped in a wildly different fate. Their surfaces tell stories written in temperature, pressure, wind and silence. These are not worlds of comfort. They are not places for breathing or walking without a suit. But each one reflects something vital, about heat, about hope, and about how planets change. We begin with Mercury, the smallest of the three and the closest to the Sun. It's a planet that lives too near the fire, baked and bombarded, its airless surface exposed to both searing heat and frigid cold. Because it spins slowly and lacks a protective atmosphere, Mercury experiences dramatic extremes. One side scorches at nearly 430 degrees Celsius during the day, while the night side plunges to almost minus 180. The difference is sharper than between boiling metal and frozen gas. Mercury has no weather, no erosion, no wind to soften its features. What remains is raw and ancient. Craters lie layered upon craters, some as wide as countries, some as old as the solar system itself. There are cliffs that stretch for hundreds of kilometres, thought to be scars left as the planet shrank slightly, its interior cooling and contracting over billions of years. It has no moons, no clouds, just rock, silence, and sunlight. A quiet testament to what happens when a world is stripped bare. And yet, even here, in this world that seems too close to destruction, there is beauty. Subtle ridges, delicate shadows, traces of ancient lava plains, a kind of stoic stillness. Mercury endures. Next comes Venus, a world wrapped not in silence, but in mystery and deception. To the naked eye, Venus is the brightest planet in the sky, a jewel that can outshine everything but the moon. Early astronomers believed it might be Earth's twin. It's similar in size and density. It has mountains, volcanoes, clouds, but the resemblance ends quickly. Venus is a world of unrelenting heat. Its thick atmosphere traps solar energy with brutal efficiency, creating a greenhouse effect so powerful that temperatures on the surface soar above 460 degrees Celsius, hotter even than Mercury, despite being farther from the Sun. That atmosphere is composed mostly of carbon dioxide, with clouds of sulfuric acid swirling high above. Rain doesn't fall to the ground, it evaporates mid-air. The pressure is crushing, more than 90 times that of Earth's atmosphere. To stand on the surface would be like diving a kilometre deep beneath the ocean, while being cooked alive. And yet, beneath that blanket of poison and pressure lies a landscape shaped by geology. Vast highlands, deep basins, thousands of volcanoes, many likely still dormant rather than dead. Venus may be a warning, a portrait of what a runaway greenhouse effect can become, but it's also a mystery. We don't fully understand how it evolved so differently from Earth, or whether it once had oceans, clouds of water, even conditions for life. Perhaps it lost those things slowly, like breath held too long. Only a few spacecraft have touched Venus's surface, and none survived more than a few hours. The heat destroyed circuits, the pressure crushed metal, the atmosphere corroded lenses. But in those brief moments, we caught glimpses of a strange world. Yellow skies, fractured rocks, distant ridges fading into haze. Venus, in its beauty and violence, reminds us that likeness does not mean safety, that a familiar size and orbit do not guarantee a familiar fate. Finally we turn to Mars, the red world, the dust-covered wanderer that has captured human imagination for centuries. Smaller than Earth, colder than our deserts, Mars is a world caught between worlds. Not entirely dead, but not exactly alive. It has seasons, polar ice caps, and a sky that turns a dusky orange at dusk. It has canyons far deeper than the Grand Canyon, volcanoes higher than Everest, and ancient riverbeds carved by water that has long since vanished. Unlike Venus, Mars has a thin atmosphere, too thin to breathe, yet just thick enough to host windstorms and drifting dust. That dust gives the planet its rusty colour, rich in iron oxide. It also makes Mars eerily quiet, a place where sound moves slowly, muffled by the thin air. But what makes Mars truly fascinating is its potential in both directions, backward and forward. In the past, Mars may have hosted flowing rivers, shallow seas, and perhaps even microbial life. Some of its oldest rocks suggest the presence of clay, formed only in the presence of water. In the present, scientists search for traces of that ancient habitability. In the future, we wonder whether we might step foot there, live there, perhaps even make it home. Mars is already home to our machines. Rovers like Curiosity and Perseverance trundle across its surface like careful explorers, their wheels pressing patterns into untouched soil. They take samples, snap photos, listen to the wind, and scan for signs of life. Above them, small helicopters flutter through the thin air, reminders that even in the coldest places, our Curiosity finds a way to fly. Of the three, Mars is the quietest, not in terms of sound, but in emotional tone. Mercury endures, Venus punishes. But Mars waits. There is something almost melancholic in its silence, a whisper of what once was, or what might be again. And in that stillness we recognise something of ourselves, a longing to know, to reach, to understand. So here, among the inner worlds, we see not just planetary science, but three paths. A planet too close to the flame, a planet that lost its balance, a planet on the edge of becoming something more. And behind them all, Earth, still blue, still alive, still waiting beneath a sky full of warning and wonder. Beyond the rocky planets and the delicate warmth of the inner system, the solar system opens wide. It stretches into cold space where the sunlight fades, and gravity gathers matter not into hard crusts, but into vast swirls of gas and ice. Here, the worlds are enormous, layered in cloud and wind, adorned with moons, storms and rings. These are the outer giants, Jupiter, Saturn, Uranus and Neptune. They do not invite visitors in the usual sense. You cannot land on their surfaces, for they have none. They are weather without ground, but from afar they are magnificent. We begin with Jupiter, the king of the planets. Twice as massive as all the others combined, Jupiter is a world of roiling gases and deep hidden secrets. Its upper atmosphere is striped with clouds of ammonia and other exotic compounds, moving in powerful bands. These stripes are not just colour, they're jet streams, travelling in opposite directions, shearing and twisting through the upper layers. Lightning flickers within their folds, and caught within one southern band, a storm larger than Earth swirls endlessly. The Great Red Spot has raged for over 300 years, a slow and ancient cyclone in a world where storms have no ceilings and no walls to contain them. Beneath those clouds lies pressure, then more pressure, until hydrogen itself changes form, becoming liquid, then metallic, behaving more like a conductor than a gas. We don't know exactly what lies at Jupiter's centre. Perhaps a dense rocky core. Perhaps something stranger. Its gravitational pull captures dozens of moons, some familiar, some still being discovered. One of those moons, Europa, holds particular interest. Beneath its icy crust, astronomers believe there is a deep global ocean kept liquid by tidal heating. In that ocean, shielded from sunlight, life might find a way. Not like life on Earth, but perhaps no less real. Bacteria, chemosynthetic organisms, tiny swimmers beneath frozen waves. If they exist, they might be the solar system's oldest secret. Then we glide towards Saturn, a softer giant, pale gold and hazy, but dressed in the most delicate adornment in the solar system. Saturn's rings are composed of ice and dust, some grains no bigger than sand, others as wide as houses. They shimmer in orbit, tilted like a great cosmic halo. From a distance they look solid. Up close, they're not even a complete structure, just a coordinated ballet of debris, shaped by the planet's gravity and the influence of nearby moons. Saturn is less dense than water. If there were a bathtub large enough, it would float. Of course, Saturn is far too enormous, and the universe far too wild for such daydreams. But the fact remains, it is massive, majestic, and yet strangely gentle in appearance. And then there is Titan, Saturn's largest moon. It is shrouded in an atmosphere thicker than Earth's, filled with methane and ethane, and it rains, not water, but liquid hydrocarbons. Rivers flow there, lakes, rest in basins. A cycle of evaporation and precipitation unfolds, eerily familiar yet entirely alien. Titan is the only place beyond Earth known to have stable liquid on its surface, but it is far too cold for water to play its usual part. Instead, it is methane that flows, a world of golden fog and dark seas. Next comes Uranus, a world of peculiarities. Its colour is a gentle blue-green, caused by methane absorbing red light in its atmosphere. But it is not just its colour that sets Uranus apart, it is its tilt. Uranus lies almost on its side, spinning like a rolling barrel rather than a top. This odd orientation may be the result of a colossal collision long ago. Whatever the cause, it gives Uranus strange seasons. For part of its long year, about 84 Earth years, each pole is bathed in constant sunlight, while the other endures a long, dark winter. Despite its distance and its quiet colour, Uranus is not still. Beneath the atmosphere, layers of ice and slushy water likely swirl around a rocky core. Magnetic fields flicker in odd directions, and though its winds are not as famous as those on Neptune, they still reach speeds of 900 kilometers per hour, unseen gales beneath a glassy calm. And at the edge of this family we find Neptune, the farthest of the giants, deep blue, mysterious and powerful. Neptune's winds are the fastest in the solar system, more than 2,000 kilometers per hour. They tear across the planet in supersonic spirals, forming dark spots that come and go. It is a place of energy, despite its frigid temperatures and enormous distance from the sun. Like its cousin Uranus, Neptune has a retinue of moons. The largest, Triton, orbits in the opposite direction of the planet's spin, an unusual behaviour that suggests Triton was once a wandering object, captured by Neptune's gravity. Triton is cold beyond imagining, yet geysers of nitrogen still erupt from its surface, powered by internal heat. Even here, so far from warmth, activity continues. The cosmos never truly rests. And behind them all, far behind, yet also always at the centre, we find the Sun. Not the Earth-sized disk we see rising and setting each day, but the real star. A ball of nuclear fire burning 100 times wider than our planet, composed mostly of hydrogen and helium. Every second it fuses hundreds of millions of tons of hydrogen into helium, releasing a flood of energy that streams across space, lighting every planet and warming their surfaces. It's easy to forget that this warmth, so familiar and gentle to us, is born from fusion, the same process that powers hydrogen bombs, yet the Sun handles it with calm, continuous control. On its surface, sunspots come and go, cooler regions in the photosphere. Flares leap into space, and coronal loops arc above the solar surface like glowing ribbons of heat. The corona itself extends far into space, thinner than air, but hotter than the Sun's own surface. And from all this, a steady stream of particles flows outward, the solar wind touching every planet, every moon, shaping the boundaries of the solar system. The Sun does not roar, it does not explode, it simply shines, patiently, persistently, turning fuel into light, light into heat, and heat into life. It anchors the dance of planets, it defines the day, it pulls comets from the deep, it lit your cradle, and it will one day light your grave. And in this moment, as we gaze back from the frozen edges of the solar system, it gleams like a coin in the dark, steady, golden, and quietly burning. Out past the planets and the Sun's golden reach, beyond the moons and silent satellites, lies a very different kind of space. Not empty, not barren, but softly filled. Here, between the stars, are great cosmic clouds, sprawling, ethereal, and impossibly large. These are nebulae, veils of gas and dust suspended in the galactic dark, stretched across light years like brushstrokes painted in silence. You may have seen photographs of them, roses of colour blooming in blackness, vast cathedrals of pink, green and violet swirls, full of pockets and curls and light. But what are they really? And why do they look the way they do? A nebula, in its simplest sense, is a cloud. But unlike the ones drifting lazily above our heads on Earth, these clouds are made of hydrogen, helium, trace elements, and cosmic dust. Spread out across unimaginably vast distances, they appear faint or even invisible to the human eye from Earth. But when captured by telescopes like Hubble or Webb, and seen through wavelengths beyond our own limited vision, they reveal their structure and subtle fire. Some shine by their own light, called emission nebulae, because nearby young stars excite the hydrogen atoms, making them glow with a rich, warm hue. Others are reflection nebulae, glowing not from within but by scattering the light of nearby stars, often in softer, bluer tones. And some are dark nebulae, shadowy forms outlined not by brightness, but by what they obscure, like fog blotting out a city skyline, their shapes made visible by what they hide. And yet these clouds are not just beautiful, they are busy. Nebulae are the cradles of stars. Within their folds, regions of slightly denser gas collapse under their own weight, slowly but surely, pulled inward by gravity. The process takes millions of years, and in the meantime, something extraordinary begins to unfold. Let's start with a familiar one, the Orion Nebula. Even with a small telescope from Earth, you can glimpse its glow as a fuzzy patch in Orion's sword. It lies about 1,350 light-years away, but its influence feels closer. This nebula is a stellar nursery, home to thousands of young stars, some still forming inside dense cocoons of gas. The images captured by the Hubble and Webb telescopes show arcs, ripples, and dark pillars reaching upward, sculpted by the intense radiation from massive newborn stars in its core. That radiation not only lights up the cloud, it carves into it, creating hollow spaces and sharp edges, shaping the very environment that birthed it. Another stellar nursery called S106 has the soft hourglass shape of something squeezed gently in the middle. It glows in infrared, where Webb's vision can see past the cooler dust. At its centre, a massive young star has just turned on, igniting its fusion engine and beginning to push outward against the gas from which it formed. The result is a glowing cloud shaped by light, heat and wind. And then there's the Lagoon Nebula, another glowing region of hydrogen stretching across 100 light years. It's full of infant stars, shock waves and knots of gas. It looks like a seascape made of light, as if someone poured pink and violet ink into still water and let it bloom outward, undisturbed. All across its span, stars are being born, quietly and without haste. But how do we see these places at all? After all, the light we receive from them is faint, so faint that our eyes would never detect it unaided. That's where space telescopes come in. Instruments like Hubble and Webb don't just take snapshots. They collect light across many wavelengths, some visible, many not. Infrared, ultraviolet, even radio and X-rays. Each kind of light reveals different layers of the nebula's story. Then that data, streams of numbers, patterns of energy, is translated into colour. Not to deceive, but to clarify. Scientists assign hues to wavelengths. Red for the long, lazy waves of infrared, blue for ultraviolet, green for excited oxygen, purple for ionized hydrogen. These colours don't mimic what you'd see with your eyes. Instead, they unveil what your eyes could never see at all. The result is not just a photograph, but a visualization, a map of structure and energy made visible. That's why the colours of space are so dreamlike. They don't belong to sunsets or oceans or paint boxes. They belong to electrons leaping between energy levels, to atoms glowing under distant pressure, to light that has travelled for hundreds or thousands of years before finally arriving here, in the mirror of a telescope's lens. Each image is a record of light's long journey. When you look at the Orion Nebula, you are seeing light that left it over 1,000 years ago. When you gaze at the Lagoon Nebula, you're watching a scene that occurred long before telescopes were even imagined. In this way, nebulae are not just distant, they are ancient. Their beauty is not just vast, but old. They carry memory in their glow, and yet that glow is temporary. Nebulae do not last forever. As stars form, they consume the gas and dust that surround them. Stellar winds from massive newborns begin to blow the cloud away, thinning it, tearing holes through it. Over time, the nursery becomes a neighbourhood. The glowing cloud fades, and what remains is a scattering of stars, some hot and blue, others smaller and cooler, drifting slowly apart. In these delicate clouds, we find the first pages of stellar history. Not explosions, not violence, but softness, patience, time folded into light. They are not places you could walk or land or breathe, but they are real, and they are part of us. Every atom in your body came, at some point, from stars that began in clouds like these. You are not made of Earth alone, you are made of nebulae. Nebulae may look soft and dreamlike, but within their folds, something powerful is always at work. Quiet, invisible, persistent. That force is gravity, and though it makes no sound, it has shaped everything you've ever known. Your body, the oceans, the planets, even time itself. In the delicate chaos of a nebula, gravity is the sculptor, carving structure from cloud, giving form to the formless. It begins gently with a whisper, a slight density here, a clump of gas there. Nothing dramatic, just imbalance, just enough mass in one spot to start pulling inward. This process, called gravitational collapse, marks the beginning of a star's life. Within a vast cloud of hydrogen and dust, there are always places where the material is just a little thicker. That thickness gives it slightly more gravitational pull than the surrounding gas, which causes more material to drift toward it. The more that gathers, the stronger its pull becomes. A feedback loop begins, and what was once just a misty pocket becomes a slowly tightening knot. Over tens or even hundreds of thousands of years, it collapses inward, gaining density and heat. At the centre, the pressure rises. The molecules, now crammed together, begin to jostle violently. A kind of internal friction builds, not enough yet to create light, but enough to create hope. This early structure is called a protostar, a star in waiting. It doesn't shine like our sun, not yet, but it's no longer just cloud. It's becoming something else. Around it, a spinning disk of gas and dust begins to form. Some of this will feed into the growing star. Some of it will eventually form planets, moons, asteroids, comets. The entire solar system in miniature begins as a whirling plate of dust. The shape of the surrounding nebula changes too. As the protostar grows and heats up, it begins to emit radiation and wind, streams of particles that push outward, carving cavities in the surrounding gas. These winds and jets collide with the material around them, creating glowing arcs, ridges, and dark fingers of dust. What you see in images like the Pillars of Creation or the Bubble Nebula are not abstract shapes or accidents. They are sculptures made by young stars pushing against their birth clouds. The Bubble Nebula, for instance, is exactly what it sounds like. A nearly perfect sphere glowing softly in pinks and violets. At its heart is a massive star, 40 times the mass of our Sun, pouring out radiation. That radiation pushes outward with such strength that it carves a literal bubble into the surrounding gas. The edges of the bubble glow because the radiation from the central star excites the atoms at the boundary. It's a portrait of motion frozen in light, expansion held still, just long enough for us to witness. Gravity's work, however, doesn't stop with one star. In many cases, the collapse of one region triggers the collapse of others nearby. Like raindrops forming on a window, these regions multiply, forming clusters of stars, some massive, some small. The more massive stars tend to form quickly and burn out faster. They shine hot, blue, and brief. The smaller ones take their time. Some may smoulder for billions of years before fading quietly into the dark. And throughout all this, gravity remains the quiet conductor. It does not rush. It does not hesitate. It simply continues, pulling, shaping, collapsing, igniting. But not every part of a nebula becomes a star. Some material is blown away by radiation, scattered by stellar winds, or left adrift in space. Some will eventually coalesce into planets, while some may never find a home at all, wandering dust in the deep. And we, watching from so far away, see only snapshots of this process. Because light takes time to travel, the nebulae we see now are as they were thousands of years ago. The Bubble Nebula is over 7,000 light-years from Earth. The light you see in its pictures began its journey long before paper was invented, long before the wheel turned or the first village was built. It left the star when our ancestors still gathered around fires, looking up at the night sky without knowing what looked back. In this way, light is a time machine. It allows us to see what was, even as we live in what is. And because gravity works slowly, we get to witness these great sculptures in progress. Arcs of light, fingers of dust and billowing curtains of hydrogen caught mid-gesture, like dancers paused in a cosmic ballet. There's something peaceful in that knowledge, that these clouds, so vast and slow and distant, are quietly giving birth to stars as we sleep. That the universe continues its patient work whether we are watching or not. And that somewhere, even now, a small pocket of gas is beginning to gather itself inward, unaware that in a few million years it will shine. When we look at a nebula, we're not just seeing beauty, we're seeing work. Invisible forces doing what they have always done, transforming the chaos of space into something luminous. And when we see the pillars and arcs, the shadows and shells, we are seeing the gentle handwriting of gravity, sketching its story in starlight. A star is not born when it first begins to shine. It is born in darkness, inside a cloud of gas and dust hidden from view, slowly collapsing under its own weight. For most of its early life it remains invisible, buried beneath layers of material. Heat rises at its core, the gas grows dense, the particles move faster, but still there is no light, just pressure, just waiting. And then one day, or rather, after hundreds of thousands of Earth years, the pressure and temperature at the centre of this forming star reach a threshold. Hydrogen atoms, crushed together by gravity's long patience, begin to fuse into helium. This process, nuclear fusion, releases energy in the form of light and heat. The outward pressure of this energy balances the inward pull of gravity. The collapse halts, the object stabilizes, the star ignites. From that moment on, the core of the star becomes a nuclear furnace. Every second, it transforms millions of tons of matter into energy. That energy pushes outward, eventually escaping as photons, first struggling through dense interior layers, then racing freely into space. Some of that light will travel for thousands of years, brushing past planets, glancing off moons, and eventually landing, perhaps, on the surface of a telescope mirror orbiting Earth. Some of it will reach your eyes, and so, what we see when we gaze at the stars is not their surface, not even their true age, but their light, flung out across time and distance, offering a glimpse of what once was. The moment of ignition, the transformation from protostar to main sequence star, is not explosive. It's not a supernova or a flare. It's more like the slow, steady lighting of a lantern that has been prepared with infinite care. And though we cannot watch this moment directly because it happens deep inside a cloud, behind veils of dust and gas, we can witness its effects. A cloud begins to clear. The surrounding dust glows. A cavity forms where there was once only mist. Other nearby stars may begin to shift, pushed gently by the newborn's radiance, and slowly, the dark becomes luminous. In regions like the Orion Nebula or the Trifid Nebula, astronomers have caught these stages mid-transition. They see clusters of infant stars still wrapped in their birth cocoons, some just beginning to emerge. Their light, although new to them, is already ancient by the time it reaches us. These stars may be only a few million years old, young by cosmic standards, but their glow already contributes to the illumination of entire regions. Some of these newborn stars are massive, dozens of times the size of our Sun. They burn brightly, live briefly, and shape their environments with ferocity. Others are smaller and steadier, like our own star, a yellow dwarf, calm and long-lived. These moderate stars shine for billions of years, giving life time to form and evolve on surrounding planets. As fusion begins, so does clearing. The star's radiation and winds begin to blow away the remaining gas and dust. What once hid the star now disperses. In doing so, the star sculpts space around it, pushing back on the very nebula that created it. Over time, the dusty shroud thins, revealing a young star system in formation. Around many of these stars, disks of leftover material begin to coalesce into larger clumps. Gravity begins its work again, on a smaller scale. Planets form, moons gather, rings swirl into being. A star system, complex and unique, takes shape, and yet, all of it began in silence. Not with thunder, but with pressure. Not with drama, but with waiting. The quiet miracle of fusion does not come easily. It must be earned through time and force. But once it arrives, it brings something new to the universe: enduring light. We often speak of stars as if they were eternal. They are not, but they are persistent. A typical star like our Sun will burn for around 10 billion years, steadily converting hydrogen into helium, shining with constant warmth. In that time, entire civilizations could rise and fall, entire species could appear and vanish, entire planets could form oceans, mountains, forests and stories, all under the steady breath of a single, patient flame. And when we look up at the night sky, when we trace constellations or watch a distant spark twinkle, we are often seeing these stars in their maturity. But behind every one of them lies a story like this: a dark beginning, a slow collapse, a flicker, a glow, a breath of fusion. And before that, a cloud, a nebula, a nursery, lost in the galactic dust. In a way, fusion is not just a process, it's a promise. That matter can become light, that pressure can become presence, that darkness can be transformed over time into radiance. And perhaps that's why we find stars so comforting, not because they are large or powerful or unreachable, but because they began in darkness, just like us. Somewhere, even now, in a cloud we cannot name, a new star is preparing itself. It gathers its atoms, it grows heavier, warmer. It doesn't know that it is about to shine, but it will, and when it does, its light will travel. It will move across space and time, and perhaps one night far in the future someone will look up and see it. A tiny point of a light, new and yet impossibly old, and they'll wonder where it came from. And it will have begun here, with gravity and silence and a quiet spark in the dark. If you look up into a winter night sky, perhaps when the air is cold and still, you might notice a small gathering of stars just above the shoulder of the constellation Taurus. At first glance, it appears like a misty smudge, a soft shimmer tucked beside the darkness. But with even a modest telescope, that smudge resolves into a sparkling group of stars. Blue, bright, close together, like a handful of gems cast gently across the heavens. This is the Pleiades, also known as the Seven Sisters, and it is one of the most familiar examples of an open cluster, a community of stars born together, moving together, bound for a time by gravity and by origin. Open clusters are not rare in the galaxy. In fact, most stars begin their lives this way, in shared birthplaces, carved from the same nebula, the same material, under the same conditions. Like siblings born minutes apart, they carry the same chemical signatures, the same motion through space, and for a while, the same address. Some clusters hold only a few dozen stars. Others, like Westerlund 2, contain thousands, densely packed into glittering regions still wrapped in the gases that formed them. These clusters are not permanent. Over tens or hundreds of millions of years, their stars drift apart, tugged by the gravity of the galaxy, scattered by close encounters, like children growing older and moving on. But while they are together, they offer a glimpse into the youth of the stars, and youth, for a star, means brightness and speed. The stars in open clusters are often young and massive, glowing with a brilliant blue-white light that reveals their high temperatures. They burn hotter, live faster, and radiate more intensely than older, cooler stars like our Sun. And because they are still near the clouds that formed them, these clusters often shine with the faint reflection of surrounding dust, giving them a slight haze, a glow that feels almost emotional, like morning light through mist. The Pleiades, lying just 444 light-years away, is relatively close in cosmic terms. Its stars are only around 100 million years old, young adults in stellar time. You can see its stars with the naked eye, but long exposures reveal dozens more. Tiny lights in delicate formation, framed by the faint sheen of a reflection nebula. Though called the Seven Sisters, There are many more than 7 stars in this family, and like all families, they won't stay clustered forever. Another open cluster, the Hyades, lies nearby in the sky. It is older than the Pleiades, about 600 million years, and already beginning to disperse. Its stars are farther apart, its edges softer, but the motion of its members through the galaxy remains coherent, a lingering signature of their shared origin. They are like leaves drifting in the same current, no longer clinging to the tree, but still following the shape of its fall. And then there is Vesterland too, a younger and more energetic cluster located about 20,000 light-years away in the constellation Carina. Buried deep within the Carina Nebula, Vesterland too is still partially hidden by the gas and dust from which it formed. Its stars are massive, luminous, and short-lived. They burn with such power that their radiation sculpts the surrounding cloud into complex forms, ridges, waves, and cavities. The light from Vesterland too may be young, but it carries a voice that echoes with purpose. These stars were born not just to shine, but to shape. That shaping is part of what makes open clusters so fascinating. They are not static gatherings, they are places of interaction. Gravity pulling, radiation pushing, stars influencing one another with heat, wind and magnetism. Binary systems are common. In some cases, stars orbit so closely that their outer layers touch, exchanging material like dancers passing light between their hands. In other cases, smaller stars are ejected from the cluster entirely, flung into space like seeds on the wind. But beyond the motion and the physics, open clusters hold a quieter poetry. They are the places where starlight begins not alone, but together. They are not single flames lit in darkness, but bonfires born from shared breath. They remind us that even in the vastness of space, creation happens in company, that stars, like people, are shaped by those they begin beside. Eventually these clusters dissolve, gravity lets go, the stars drift, the tight formation loosens. Over hundreds of millions of years, what was once a luminous knot becomes a faint trail. Some stars will remain near each other, others will be drawn into different parts of the galaxy, their shared past forgotten except in the chemistry of their cores. Astronomers can sometimes trace these paths backward, reconstructing a long-lost cluster by analysing motion and metallicity. It's a kind of cosmic archaeology, finding the siblings of stars now scattered across the Milky Way. Even our own sun, it is believed, was born in such a cluster. Long ago, some 4.6 billion years in the past, it formed in a nebula like Orion, alongside dozens or perhaps hundreds of other stars. Those siblings are now scattered across the galaxy, their light reaching other worlds, their histories invisible to us. But the fact remains, our sun too was not always alone. So when you look up at the Pleiades, or at a long exposure photograph of Vesterland too glowing inside its nebula cocoon, you are seeing the memory of togetherness. A moment in time when stars shared space, motion and birth. It is a fleeting phase in the life of a star, but a meaningful one. A moment of closeness before the long journey outward begins, and maybe in that there is a comfort. That the universe, so often quiet and cold, begins in moments of shared light. If open clusters are the nursery rooms of the cosmos, full of young stars, wide-eyed and glowing, then globular clusters are its silent monasteries. Distant, massive and densely packed, these ancient spheres of stars hover like forgotten ornaments in the galactic halo. They do not flash with the blue-white intensity of youth. Instead, they shimmer in gold and amber, the cool light of stars that have burned slowly for billions of years. While open clusters disperse over time, globular clusters endure, held together by gravity and age, containing some of the oldest known stars in the universe. Globular clusters are not small. They often contain hundreds of thousands, sometimes even millions of stars. Yet, compared to the sprawling arms of galaxies, they are tightly bound, condensed into spheres no more than a few hundred light-years across. If you lived inside one, and astronomers have often dreamed what that would feel like, you would see a night sky crowded with stars. Not just pinpricks, but blazing orbs so close together that shadows might never fully form. The nearest star to you might be just a fraction of a light-year away, and the entire sky would gleam with a warm, crowded hush. One of the most beautiful and well-studied globular clusters is Messier 13, also known as the Great Hercules Cluster. Located around 22,000 light-years from Earth, it contains over 300,000 stars in a space barely 150 light-years wide. Through a telescope, it appears as a dense glowing ball with stars packed tighter and tighter toward the centre, like fireflies clustering at the heart of a lantern. And it's not unique. The Milky Way has at least 150 known globular clusters, and likely more still hidden behind clouds of dust and the brightness of the galactic plane. Unlike open clusters, which are usually young, mere millions of years old, globular clusters are ancient. Most are over 10 billion years old, with some pushing close to 13 billion, nearly as old as the universe itself. The stars within them are typically population 2 stars, old, low in metal content, and slow burning. These stars formed when the universe was still new, when heavier elements were scarce, and the first waves of stellar birth had only just begun. In their light, we glimpse the early universe, not in theory or simulation, but directly, as if a door has been left ajar to a distant past. These clusters do not sit inside the bright disk of the galaxy like planetary neighbourhoods. Instead, they orbit the galactic centre in a vast spherical halo, passing above and below the galactic plane in slow, looping arcs. Some take hundreds of millions of years to complete a single orbit. In this way, they serve as reminders of the Milky Way's shape and structure, like glowing punctuation marks outlining the unseen edges of our galactic story. Because of their age and richness, globular clusters are valuable to astronomers not just as objects of beauty, but as tools. By studying the stars inside them, especially their composition and brightness, scientists can better understand the early conditions of the Milky Way and of galaxy formation in general. They are quite literally time capsules, preserving conditions from the universe's earliest chapters. There's also something intriguing about their symmetry. While galaxies swirl and spiral, and open clusters stretch and drift, globular clusters seem to resist that chaos. They are round, balanced. Their stars orbit the common centre in complex interwoven paths, held fast by mutual gravity. Yet they do not collapse inward entirely. Instead, they remain in stable, glowing equilibrium, dense in the centre, diffuse at the edges, but whole. Occasionally, within these dense environments, something unexpected happens. Stars can interact closely, even collide. In such close quarters, chance encounters are more likely. And from those interactions, new kinds of stars may form. Blue stragglers, for example, which appear younger and hotter than the others around them. These are thought to be the result of mergers, 2 old stars joining to form something brighter and seemingly younger. In a community that is billions of years old, these few rebellious lights stand out like sudden sparks. And perhaps there's something poetic in that. In a place defined by age and stillness, bursts of renewed energy can still emerge. The cluster does not stagnate. It changes, slowly, subtly, but surely. If you observe a globular cluster through a powerful telescope, you might find yourself mesmerized by the density. The stars are so close that it's difficult to see them as individuals. They become a texture, a weave of light. But look longer, and you begin to notice their variety. Some are cooler and redder. Some shine with a soft gold. Some pulse faintly as variable stars, their brightness shifting gently over time. Each one is a sun, with its own history, its own quiet pulse. And all of them, together, form a community of light bound by gravity, by time, and by the space between them. When we look at these ancient structures, we're not just seeing stars, we're seeing continuity. The fact that something so old, so densely packed, and exposed to the chaos of galactic tides, could survive for billions of years without breaking apart is a quiet kind of miracle. And it reminds us that the universe is not just about beginnings and endings, it's also about endurance, about holding together even when time stretches into incomprehensible scales. So while open clusters tell us about youth and motion, globular clusters whisper about patience, about what lasts, and about the kind of beauty that doesn't fade but deepens with age. In their light, we glimpse not just where stars come from, but what they become when they endure. Every star begins the same way, in darkness, in dust, in quiet collapse. But the path that unfolds from that beginning depends on something as simple and as fateful as mass. A star's destiny is written not in prophecy or design, but in the amount of matter it gathers to itself before fusion begins. That initial weight decides everything: how brightly it will shine, how long it will live, what kind of death it will have, and what it will leave behind. A low-mass star, like our own sun, spends the vast majority of its life in what's called the main sequence phase, burning hydrogen into helium in its core, shining with calm consistency. This phase can last for billions of years. Our sun, for example, is about halfway through its roughly 10 billion year lifespan. During this time, it expands only slightly, growing slowly brighter as it consumes its fuel, but it remains stable, a quiet and dependable presence in the solar system. But stars do not burn forever. Eventually the hydrogen in the core runs low. As fusion slows, the delicate balance between outward pressure and inward gravity begins to shift. The core contracts, and the outer layers respond by expanding. The star becomes a red giant, enormous, cool on the surface, but fiercely hot at the centre. In this phase, the star begins to fuse helium into heavier elements, creating carbon, nitrogen, and oxygen. The outer layers swell to encompass any nearby planets. One day, billions of years from now, Earth itself will be engulfed in this red tide, and yet even this expansion cannot last forever. When the helium is spent, fusion can no longer proceed. Not in stars of this size, the core, now dense and inert, contracts again. The outer layers, loosely held, drift away into space, forming a glowing shell of gas known as a planetary nebula, a term that has nothing to do with planets and everything to do with early astronomers' telescopes, which saw these rounded shapes as reminiscent of Uranus or Neptune. The central core, no longer burning, becomes a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. No fusion burns within it. It simply glows with the residual heat of its past. Over trillions of years it will cool and darken, eventually becoming a black dwarf, though the universe is still too young for any to yet exist. This is the quiet fate of stars like our sun. No explosion, no grand finale, just light, slowly fading into silence. But not all stars go so gently. For those that begin their lives with much more mass, 8 times or more the mass of our sun, the story ends quite differently. These massive stars burn brighter and faster, consuming their fuel in just a few million years. Their cores become hot enough not only to fuse helium, but to keep going, creating carbon, oxygen, neon, magnesium, silicon, and eventually iron. Iron, though, marks a kind of final wall. Unlike lighter elements, fusing iron does not release energy, it consumes it. And when a massive star's core fills with iron, fusion halts completely. Without the outward pressure of fusion, gravity wins. The core collapses in a fraction of a second. The outer layers follow, crashing inward at immense speeds. Then, just as quickly, they rebound. This violent implosion and explosion produces a supernova, one of the most energetic events in the universe. In that moment, the star outshines its entire galaxy. Shockwaves race outward. Heavy elements are forged. Gold, uranium, all the things fusion could not produce before. These elements are scattered into space, seeding the next generation of stars, planets, and life. What remains at the centre depends again on mass. Some collapsing cores become neutron stars, tiny, incredibly dense remnants no wider than a city but more massive than the Sun. Others collapse further still, past even the pressure of neutrons, becoming black holes, where gravity reigns so completely that not even light can escape. It is strange, perhaps, to think of something as eternal seeming as a star having an end. But the universe is made not just of beginnings, but of cycles. A star is born from dust, lives in light, and returns its material to space. That returned matter may form new clouds, new stars, new planets. And so, in a very real sense, death is not destruction. It is transformation. The calcium in your bones, the iron in your blood, the gold in your jewellery, all were once formed in the hearts of stars, and many of those stars died in supernovae long before Earth even existed. So when you look at a glowing planetary nebula, or at a fading white dwarf, or at the echo of a supernova remnant drifting across the sky, you're witnessing a kind of cosmic recycling. Endings are beginnings, just told in reverse. And maybe that's the deepest comfort the stars can offer, that everything returns, that nothing is lost, that the same forces that pull stars apart also pull them together. Gravity, fusion, time and dust, from starlight to shadow and back again. In this dance of heat and pressure, birth and collapse, you are not an outsider. You are made of this. You carry the legacy of 1,000 stars in your cells, and the light you see above you is not distant. It is ancestral. It is your story, written in fusion and flame. If you've ever stood beneath a truly dark sky, far from the hum of cities under a blanket of stillness, you may have seen it. A soft band of light stretching across the heavens, too faint to illuminate anything, but too present to ignore. It is not made of clouds or mist or imagination. It is the Milky Way, our home galaxy, seen from the inside, a river of stars so vast, so densely packed, that their combined glow becomes a silken smear across the night. We live inside a galaxy, but we cannot see it whole. We are part of the pattern, embedded within one spiral arm, drifting in circles that take hundreds of millions of years to complete. Like standing in the middle of a vast forest, we can glimpse the trunks nearby, the rise and fall of the land, the scatter of leaves and needles, but we cannot see the entire shape of the woodland. Not with our eyes, not all at once. Still, through patient observation and careful mapping, astronomers have begun to sketch the form of our galactic home. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years in diameter, with a central bulge and several sweeping arms that curl outward like petals of a pinwheel. Our own solar system lies in one of these arms, the Orion arm, about 27,000 light-years from the galactic centre. That centre, shrouded in dust and mystery, harbours a supermassive black hole known as Sagittarius A, whose presence can be inferred by the way stars whirl around it like dancers around a silent drum. We move, though we rarely notice it. The entire solar system orbits the galactic core at roughly 828,000 kilometers per hour, completing one full revolution every 225 to 250 million years, a journey known as a galactic year. The last time Earth was in this same position relative to the centre of the galaxy, dinosaurs roamed vast fern-covered plains, and flowering plants had only just begun to bloom. Though the galaxy is vast, our understanding of it has become increasingly precise, thanks to missions like Gaia, the European Space Agency spacecraft that has been mapping the positions, motions and distances of over 1 billion stars in the Milky Way. Gaia's data has allowed astronomers to build a detailed, dynamic map of our galaxy in motion. A ballet of stars sweeping through space, each with its own trajectory, its own rhythm. Through Gaia, the forest becomes a moving organism, not a frozen backdrop. And yet, even with these advances, we remain inside the story. We cannot step outside and look back. All our images of spiral galaxies, those elegant wheels of light against velvet black, are glimpses of other galaxies seen from afar. When we look at galaxies like Andromeda, Triangulum or Whirlpool, we are seeing what we cannot see of ourselves. We're looking into mirrors that are similar but never quite the same. We infer our own shape from their clarity. Among those galactic reflections, Andromeda is the closest in scale and size. It lies just 2.5 million light-years away, close in cosmic terms, and is on a slow, inevitable collision course with the Milky Way. This is not an impending catastrophe, but a graceful convergence that will unfold over the next 4 billion years. When they meet, the two galaxies will not crash in the way we think of collisions. Their stars are so far apart that most will pass by untouched. Instead, their gravitational fields will tangle, their shapes will distort. Gas and dust will be thrown into new patterns. Star formation will surge. Eventually the two will merge into a single, larger elliptical galaxy. Some have named the future child Milkomeda. It's humbling to realise that even galaxies move, even galaxies change. And while we often picture the universe as a grid of distant galaxies dotting a flat canvas, the truth is more fluid. Galaxies orbit one another. They form clusters and superclusters. They're pulled and stretched by dark matter, twisted by time, and shaped by the very gravity they emit. The Milky Way is part of the Local Group, a small gathering of more than 50 galaxies bound loosely together, which itself is part of the Virgo supercluster, a much larger structure that contains thousands of galaxies, including great names like Coma, Hydra, and Centaurus. And even these superclusters are just threads in the cosmic web, a network of filaments and voids that stretch across the universe like glowing nerves through darkness. In the grandest sense, our home galaxy is not just a place, it is a position, a node in a web too vast to map in full, but delicate enough to be traced through time and light. And yet, amid all this motion, all this scale, the Milky Way still shines with a kind of intimacy. It is where every human story has taken place, where every tree has grown, where every star we have ever named has burned. It holds the sun and moon. It holds Earth. And though we may one day leave Earth behind, and perhaps even our solar system, we will remain for a long time still residents of this galaxy, one of billions, yet still ours. So the next time you find yourself beneath a sky dark enough to reveal that arc of stardust stretching from horizon to horizon, pause a moment. That river of light is not just a backdrop, it is a bridge, a structure of time, gravity, and fire, and it's yours, not in the sense of ownership, but in the sense of belonging. You live here, you always have. From a distance, galaxies seem serene, spirals and ellipses floating through stillness, each one a glowing island of stars in a vast, dark sea. But this stillness is an illusion. If you had the patience to wait millions of years and the perspective to look down from outside time, you'd see that galaxies are not fixed. They twist, they reach, they collide, they fall into one another like dancers in slow motion, each step stretched across eons. Galaxies move not just individually but in groups. They are bound by gravity into families called clusters, and within these families, interactions are inevitable. Sometimes they pass each other gently, like strangers brushing shoulders in a crowd. Other times they tangle, arms stretching, cores warping, clouds of gas drawn out into long luminous streams. These interactions can last for billions of years and can completely reshape the galaxies involved. One of the most iconic examples of a galaxy caught mid-gesture is the Whirlpool Galaxy, also known as Messier 51. Located about 31 million light-years from Earth, it is a near-perfect spiral, its arms curling outward with elegance, like ripples frozen in time. But look a little closer, and you'll notice something pulling at it, a smaller companion galaxy, caught in its gravitational web. The smaller galaxy is orbiting the Whirlpool's centre, and in doing so, it's stirring the stars and dust, triggering bursts of star formation where the gas is compressed. These glowing regions, visible in pink and blue, are signs of new stars being born, lit by the very chaos of the encounter. This is what makes galactic interactions so fascinating. They're both violent and creative. Though we speak of collisions, actual star-to-star impacts are vanishingly rare because of the vast distances between stars. Instead, it's the galaxy's gas and dust that interact, sloshing, compressing, heating. These encounters disturb the calm of star nurseries and often awaken new waves of stellar birth. A collision does not extinguish a galaxy's light. It often increases it. And then there is Stephan's Quintet, a group of 5 galaxies located about 290 million light-years away in the constellation Pegasus. It is not a tidy arrangement. It is a picture of drama and disruption. Of the 5, 4 are genuinely close together in space, bound by gravity and already interacting. The 5th, though it appears nearby in the image, is actually much closer to us. A photobombing foreground galaxy, aligned by coincidence. But that illusion does not diminish the reality of what's unfolding. In Stephan's Quintet, you can see tidal tails, long drawn-out streams of stars that have been pulled away by gravitational encounters. You can see distorted shapes, warped spiral arms, and shock waves of light. One of the galaxies, NGC 7318b, is crashing into a pool of intergalactic gas, sending out a shock front thousands of light-years wide. In recent images captured by the James Webb Space Telescope, the region reveals itself in stunning detail, clouds of dust curling and glowing with warmth, evidence of active star formation and cosmic upheaval. These collisions are not rare, but they are slow. If you could watch a time-lapse stretched over hundreds of millions of years, you'd see these galaxies spiraling into one another, merging, reshaping, and eventually settling into a new form, no longer separate entities but one larger galaxy, changed forever by the dance. Andromeda and the Milky Way, as we noted earlier, are on such a course. Their mutual gravity is pulling them together, and 4 billion years from now they will merge, not with fire and noise, but with elegance. The night sky on Earth, or whatever world bears witness then, will be filled with glowing arcs and tidal streams. Stars from both galaxies will settle into new orbits. Gas clouds will collide, and stars will form in furious waves. It will be, in every sense, a rebirth. But it's not only collisions that define galactic life. Even without mergers, galaxies are constantly shaped by internal dynamics, rotating, vibrating, churning from the inside. Spiral arms are not permanent fixtures, but patterns formed by waves of density, like traffic jams in space where gas and stars accumulate temporarily before moving on. Bars and bulges, rings and voids, all of these features evolve over time. Galaxies age not in silence but in motion. These cosmic structures are also influenced by things we cannot see, most notably dark matter. Every galaxy is believed to sit inside a massive halo of dark matter, an invisible scaffolding that helps hold it together. Though we cannot detect dark matter directly, we can see its influence in the way galaxies rotate, in the speed of their outer stars, and in the lensing of light from more distant objects behind them. Galaxies, then, are not just made of stars and gas. They are embedded in a larger unseen architecture, one that shapes their lives and interactions in ways we're only beginning to understand. When we look at images of galactic collisions or twisted arms or glowing knots of stars, we're seeing more than just beauty. We're seeing the quiet, ongoing work of time and gravity. We're seeing how even vast structures change, how forms bend and blend, how the universe never stays still. And yet, there is no rush. A galactic collision takes hundreds of millions of years. From our perspective, it may seem like a frozen moment, but in that moment are tides of motion, of transformation, of becoming. So perhaps the next time you see an image of the Whirlpool Galaxy, or Stephan's Quintet, or Andromeda slowly reaching toward us, you'll remember that even in the coldest parts of the cosmos, there is always movement, always interaction, always creation, and just as stars are born in clouds of dust, galaxies are reshaped in waves of light. There is a photograph, perhaps you've seen it, that at first glance looks unimpressive. A dark rectangle scattered with tiny specks, some faint, some glowing more brightly, arranged with no obvious pattern. It could be mistaken for digital noise or static, and yet it is one of the most extraordinary images ever captured by humanity. This is the Hubble Ultra Deep Field, and nearly every single speck you see in it is not a star, but an entire galaxy. To take this image, astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky in the constellation Fornax, a region so small it would have been obscured by a grain of sand held at arm's length. They kept the telescope fixed on that dark window for over 11 days, letting it collect the faintest light it could find. What it revealed stunned even the scientists who planned the observation. The sky, it turns out, is not mostly empty. It is saturated with galaxies, thousands of them, each one filled with billions of stars. And some of the galaxies in that image are ancient. Their light began its journey more than 13 billion years ago, just a few 100 million years after the Big Bang. In other words, the image is not just a deep look into space, it is a deep look into time. You're not seeing what these galaxies look like now. You're seeing what they looked like when the universe was young, when stars were just beginning to form, when the very first heavy elements were being created in the hearts of newborn suns. The Hubble Ultra Deep Field reminds us of something quiet but profound. Light travels at a finite speed, and because of this, distance becomes a form of memory. The farther away something is, the older the light we receive from it. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. But when you look at the galaxies in the ultra-deep field, you're peering across billions of years. The telescope becomes not just a lens, but a time machine, revealing the ancient architecture of a universe still in the process of becoming. Some of the galaxies in that image are small and chaotic, irregular clumps of stars and dust that haven't yet formed the elegant spirals we see in more mature systems. These are proto-galaxies, the early attempts of gravity to gather matter into luminous forms. They are building blocks, glowing embers scattered across the cosmic dawn. Others are more familiar, small spirals or ellipticals surprisingly well formed even at great distances. These may have grown quickly, fed by rich clouds of hydrogen in the young universe, or may have merged with neighbours to gain their size and structure. There are mysteries too. Some points of light appear redder than expected, not because of their content, but because of cosmic redshift. As the universe expands, the wavelengths of light stretching across, it are also stretched, shifted toward the red end of the spectrum. This effect allows astronomers to estimate just how far and how ancient each galaxy is. The most distant ones appear as smudges of red, their photons worn thin by a universe that has been expanding since the moment of their departure. And just imagine, the light from those galaxies has been travelling for billions of years through the silence of space, crossing empty voids, brushing past stars, dodging dust clouds, slipping by entire galaxies, just to end its journey at the lens of a human-made telescope. The story it carries is not in words, but in brightness, in colour, in structure. It says, "We were here," long before you knew to look. In more recent years, the James Webb Space Telescope has extended this view even farther. Its powerful infrared vision allows it to peer through dust and detect even fainter, redder galaxies, and already it has begun to reveal galaxies that challenge our expectations, larger, brighter, and more structured than theories once predicted for such an early universe. It is as if the cosmos, like all good storytellers, has saved some of its surprises for later. But the emotional weight of these deep field images is not just scientific, it is personal. To look at the Hubble Ultra Deep Field is to feel small, yes, but also to feel connected. You're made of the same atoms that once burned in those ancient suns. You're part of the same universe that spun those galaxies into being. You are, quite literally, looking at your past, not in a metaphorical sense, but in a physical, photonic one. And perhaps what's most moving is this, that a small group of humans floating on a small world around a small star decided to point their telescope at what looked like nothing and discovered everything. That in a patch of sky where no light appeared to the eye, they found 1,000 galaxies, and in each of those galaxies billions of stars, and around those stars, perhaps planets, and around some of those planets, perhaps oceans, perhaps skies, perhaps someone else long ago looking out and wondering if they were alone. So next time you gaze at a night sky and see only darkness between the stars, remember what that darkness contains. Not emptiness, but distance. Not silence, but memory. And in that memory, a soft reminder. The universe is deeper, older, and more luminous than it first appears. You just have to keep looking. For most of human history, the question of whether other worlds existed beyond our own was more a matter of philosophy than science. The night sky offered little more than stars, unblinking, unreachable points of light, each one a mystery. The idea that some of those stars might harbour planets like Earth was poetic, perhaps even plausible, but entirely unproven. We simply didn't know, and for a long time we had no way to find out. That changed in the late 20th century, when astronomers began to detect the first signs of planets orbiting distant stars, not through direct images but through subtle shifts and flickers. What had been imagination became data. What had been a dream became a discovery. Today, we know of thousands of exoplanets scattered across the galaxy in every direction. Some orbit suns like our own, others circle stars smaller and cooler, some are blistering gas giants hugging their stars too tightly to hold an atmosphere. Others are small and rocky, perhaps wet, perhaps warm. The variety is staggering, and we are only beginning to look. Most of these worlds have been found through two primary methods. The first is the transit method, made famous by the Kepler Space Telescope. This method involves watching a star's light very carefully and waiting for it to dim ever so slightly at regular intervals. That dimming can signal that a planet has passed in front of the star, blocking a tiny fraction of its light. From the size and duration of the dip, astronomers can estimate the size of the planet and how long it takes to orbit its star. With enough transits, patterns emerge. From patterns, the planets themselves begin to reveal their secrets. The second method is known as radial velocity. Instead of watching for dips in brightness, it listens for tiny wobbles in the star's motion. As a planet orbits a star, it doesn't simply circle it. The two bodies actually orbit a shared centre of gravity. This tug-of-war causes the star to shift slightly toward and away from us, creating a change in the light's frequency, a kind of stellar Doppler effect. These shifts are incredibly subtle, but with precise instruments they can be detected, and from them we can infer the mass and orbit of the invisible companion. More recently, with improved technology, astronomers have begun to directly image some exoplanets, capturing actual photos, usually in infrared, where the light of the planet can be separated from the overwhelming glare of its parent star. These images are rare and often faint, but they are real. and they open a new kind of door, a window, not just to a dot of data, but to a place. Among the most intriguing exoplanetary systems discovered so far is TRAPPIST-1. Located about 40 light-years away, this ultra-cool dwarf star is home to 7 Earth-sized planets, 3 of which lie in the so-called habitable zone, where liquid water could potentially exist on the surface. The planets orbit close together, completing circuits of their star in just a few days, locked in a rhythmic resonance like dancers following each other's steps. If you stood on one TRAPPIST-1 planet and looked up, you might see another world hanging in the sky, large and bright, close enough to imagine crossing. Of course, habitable zone is a term full of caveats. It doesn't guarantee oceans or air or life. It simply means the conditions might be right, temperature-wise, for water to remain liquid, assuming all else is favourable. But in astronomy, maybe is a powerful word. It's a call to attention. It means a place worth looking at again, and that's what we do, we look again. With telescopes like TESS, Transiting Exoplanet Survey Satellite, CHEOPS, and the upcoming PLATO mission, we're expanding our catalogue of possible worlds. We're narrowing our search, and with the James Webb Space Telescope, we're beginning to analyse the atmospheres of some exoplanets, looking for hints of water vapour, carbon dioxide, methane or oxygen. Not proof of life, but signs that could one day point in that direction. It's hard not to wonder what these planets are like, what their skies look like, if they have clouds or oceans or winds, if they turn slowly or quickly, if they know storms or silence. And beyond that, we wonder about what we might never know, whether any of them harbour life, whether some distant creature has looked up at its own version of a sky and wondered if it was alone. But even without answers, the questions shape us. The act of searching is itself a kind of transformation. It reminds us that our solar system is not the full story, that our sun is not the only sun, that Earth is not the only possible home. In every exoplanet we find there is a mirror, not reflecting what we are, but what we could become, a reflection of possibility. And perhaps that's why these worlds hold such quiet power over our imaginations. Because in a universe so vast, so ancient and so quiet, the idea that other Earths might exist, places with warmth, with water, with weather, is not just hopeful, it is grounding. It connects us to the stars not just through light, but through the shared conditions of being. We may never visit these worlds, not in person, but we will know them. Slowly, carefully, patiently, we will listen to their light. We will learn how they move, what they are made of, what they hold close. And in that listening, we will continue to ask the question that has always echoed in the space between stars. Are we alone? And we will keep listening, because that question too is a kind of home. In our everyday lives, light is something we take for granted. It streams through windows, casts shadows across floors, glints off surfaces, and fills our eyes with colour. But when it comes to the cosmos, light is everything. It's not just illumination, it's information. Every distant star, nebula and galaxy sends us its light as a message, sometimes across billions of years. And how we read those messages depends on more than just our eyes. What we see, what we call visible light, is only a small slice of the electromagnetic spectrum. It's a narrow band nestled between infrared and ultraviolet, and it happens to be the portion our eyes evolved to detect. But the universe does not limit itself to what we can see. It radiates in radio waves and X-rays, in gamma rays and microwaves, in infrared warmth and ultraviolet bite. Each wavelength reveals a different part of the story. To understand this, imagine looking at a cloud of dust in space. With visible light you might see a soft, dark smudge, an absence, a place where stars are hidden. But switch to infrared, and suddenly the scene transforms. The dust becomes transparent. Warm objects within begin to glow. New stars appear, previously concealed. What looked like silence becomes motion. What seemed empty becomes alive. This is why so many of the most stunning images from space are not in true colour. Instead, they are often false colour or colour-enhanced images, visual translations of data captured in wavelengths the human eye can't see. These images aren't lies, they're interpretations. They take information from invisible light and render it in colours we can perceive, using consistent rules to represent temperature, composition, or structure. In some images, red might indicate cooler dust, while blue reveals hotter stars. In others, green could show ionized oxygen, and red could signal glowing hydrogen. The palette varies depending on what's being studied and how. It's a bit like taking a piece of music and turning it into a painting, not because you want to change its meaning, but because you want to express its shape in a way the senses can grasp. This process allows us to visualize things far beyond our reach. The Hubble Space Telescope, for instance, captured light in both visible and near-infrared, combining data from different filters to create those iconic, painterly views of nebulae and galaxies. But its successor, the James Webb Space Telescope, reaches even farther into the infrared spectrum, revealing cooler and dustier regions that Hubble could never see. Webb doesn't just show us more stars, it shows us the hidden scaffolding of the universe. With its finely tuned instruments, it peers into the dense hearts of star-forming regions where baby stars still nest inside their dusty wombs. It captures the glow of exoplanet atmospheres, the heat signatures of distant worlds, and the ancient light of galaxies formed soon after the Big Bang. One of Webb's early images, of the Carina Nebula, showcases this perfectly. Where Hubble saw a majestic wall of gas and light, Webb reveals deeper layers, pillars within pillars, lit from within by stars so young they're still wrapped in their natal clouds. The image is not just clearer, it is more complete, like moving from a silhouette to a full portrait. Another of Webb's gifts is its ability to see cooler objects. While stars blaze hot and bright, many of the most interesting things in space, like exoplanets, brown dwarfs, and debris disks, emit most of their energy in the infrared. These objects aren't invisible, they're simply hiding in a part of the spectrum we've only recently learned to explore. Webb doesn't just detect them, it studies them, revealing temperature, composition, and motion. Even black holes, which emit no light of their own, can be studied this way. Their surrounding material heats up as it falls inward, glowing brightly in X-ray or infrared depending on the process. And by looking at how light bends around them, a phenomenon known as gravitational lensing, we can even use them as tools to magnify the distant universe behind them. The more we learn to see in different wavelengths, the more the universe unfolds before us. It's like listening to a familiar melody played on a different instrument. The notes are the same, but the texture changes. The emotion deepens, the meaning expands. And perhaps that's the most beautiful part of this invisible spectrum, that it shows us what was always there, just out of reach. That the night sky, so often dark and still, is filled with colours and motions and structures beyond imagining. That silence is only silence until we learn how to listen differently. When you see an image from a telescope, a swirl of blues and purples, a haze of gold and crimson, it's tempting to ask, is that what it really looks like? But the better question might be, is this what it's trying to say? Because light in all its forms is a language, and our instruments, from Hubble to Webb, are translators, helping us understand a story that has always been written in brightness. So the next time you look at a nebula glowing in improbable colours, or a galaxy with radiant arcs and ghostly hues, remember that you're not just seeing light, you're seeing messages, some recent, some ancient, some in tones we were only beginning to hear. The universe speaks in wavelengths, and we are learning how to listen. When we look up into the night sky, everything seems close. The stars appear scattered across a smooth black canvas, each one a pinprick of light, suspended in the same celestial dome. It's easy to forget that they are not all part of the same layer, that some are hundreds of light years away, others thousands, and still others so distant their light began travelling toward us before humans walked the Earth. But how do we know that? How do we, from a small planet spinning in the quiet suburbs of a spiral galaxy, measure the vast distances between ourselves and the stars? We cannot walk there. We cannot stretch a ruler across space. What we use instead is far more elegant. Light and motion, geometry and physics, inference and patience. A chain of methods, each one building on the next, that together allow us to measure the cosmos. It begins with something ancient, something the Greeks understood in theory over 2,000 years ago. Parallax. If you hold out your finger and look at it first with one eye closed, then the other, you'll see it appear to shift against the background. That shift is parallax. Your eyes are a short distance apart, and that baseline allows your brain to calculate depth. Now imagine Earth as one eye, and 6 months later, on the other side of the Sun, as the other. That baseline, roughly 300 million kilometres wide, gives astronomers the leverage they need to detect tiny positional shifts in nearby stars. A star that appears slightly offset in July, compared to January, is exhibiting parallax, and from the size of that wobble, we can calculate its distance. This method works well for stars within a few hundred light years. It's precise, it's direct. But beyond that range, the angles become too small to detect with traditional instruments. To reach farther, astronomers use standard candles, objects whose brightness is known, no matter how far away they are. One class of these is Cepheid variable stars. These stars pulse regularly, and their rate of pulsation correlates with their intrinsic brightness. By observing how bright they appear to us, and comparing that with how bright they actually are, we can calculate how far away they must be. It's like seeing a familiar lighthouse in the fog. If you know how powerful its beam is, the faintness of the light tells you how much fog and distance lies in between. Another kind of standard candle is the type Gaia supernova, a powerful, predictable explosion that occurs when a white dwarf star reaches a critical mass. These events are extremely bright, often outshining their entire host galaxies for a time, and because they follow a consistent brightness pattern, they serve as excellent mileposts in the expanding universe. But the farther we go, the more we must rely not on brightness, but on redshift, a cosmological echo of motion and time. When a light source moves away from you, its waves stretch out. The light becomes redder. This is the Doppler effect, familiar to you when the pitch of a passing siren drops as it recedes. The same principle applies to galaxies. As the universe expands, distant galaxies are carried away from us, and the light they emit is stretched into longer wavelengths. The greater the redshift, the faster they're moving away, and the farther they are from us. By combining redshift measurements with our understanding of cosmic expansion through Hubble's law, which relates velocity to distance, we can estimate how far away a galaxy is. This method takes us not just across the galaxy, but into the early epochs of the universe. The galaxies we see in deep field images, faint and red and strange, are not just far, they are ancient. Together these tools form what astronomers call the cosmic distance ladder. Parallax at the bottom rung, nearby and reliable. Standard candles in the middle bridging the gap. Redshift at the top, extending our reach to the very edge of the observable universe. No single method gets us all the way, but linked together, step by careful step, they allow us to measure across scales that would otherwise be beyond comprehension. And what is a light year really, if not a unit of memory? It's not a measure of time, but of distance travelled by something that moves forever forward. Light, cast out from a source long gone. In 1 year, light travels nearly 10 trillion kilometres. So when we say a galaxy is 10 million light years away, we're saying its light has spent 10 million years in flight, crossing a landscape so vast and so empty that its message arrives only now, and only faintly. This makes the act of observation something almost sacred. When we look out, we are not seeing things as they are, but as they were. We are surrounded not by stars and galaxies in the present moment, but by layers of light time, of echoes moving outward, of stories suspended in motion. The farther we look, the deeper into history we peer. There is something quieting in that thought, that all around us the sky is full of messages that took millions or billions of years to reach us. That the night is not just dark, but full of long-travelled light. That the distances between us and the stars are real, but not unmeasurable. That even in the vastness of space, we have found ways to know we are small. That much is certain. But we are also clever and curious and stubborn. We have built tools from glass and metal, launched them beyond the sky, tuned them to frequencies we cannot hear or see. We have deciphered angles and brightnesses and shifts. And with these fragile instruments we have drawn a map, not just of where things are, but of how far they've come. And in doing so, we have come far ourselves. When we talk about seeing the universe, we're not really talking about seeing it with our eyes. We're talking about translating the invisible into the visible, about building instruments that can catch whispers of light across distances so vast they stretch the meaning of the word far. Our eyes are marvellous but limited. They see a sliver of the electromagnetic spectrum, a thin band of colour. The cosmos, however, shines in every wavelength, and so, to truly see it, we had to build eyes that could see differently. 3 of the most extraordinary of these are the Hubble Space Telescope, the James Webb Space Telescope, and Gaia. Each sees the universe in a different way, for a different purpose, and each has opened a new layer of understanding that was previously hidden in the dark. Launched in 1990, and orbiting about 550 kilometres above Earth's surface, Hubble has become almost mythic in the public imagination. For over 3 decades, it has captured iconic images of nebulae, star clusters, distant galaxies, and planetary systems. Its mirrors collect visible and near-infrared light, allowing it to observe with stunning clarity the same kinds of wavelengths our eyes are built for, but without the interference of Earth's atmosphere. From the pillars of creation to the Hubble Deep Field, its photographs have reshaped not only our understanding of space, but our emotional relationship with it. Hubble is not just a telescope, it's a storyteller, and the stories it tells are luminous. But as powerful as Hubble is, it has limits. To see farther, to see the earliest galaxies or the birth of stars still wrapped in clouds of gas, we need to see in infrared. That's where the James Webb Space Telescope comes in. Launched in late 2021 and positioned nearly 1.5 million kilometres from Earth at a place called the Second Lagrange Point, Webb is a masterpiece of engineering. Its golden mirror, made of 18 hexagonal segments, is over 6.5 metres wide, more than twice the size of Hubble's, and its instruments are tuned to capture mid and near-infrared light. This means Webb can peer through dust clouds, revealing stars and structures previously invisible. It can see light from galaxies that formed over 13 billion years ago, stretched into infrared by the expansion of the universe. In a way, Webb is not just a telescope, it is a time machine, looking back into an era when the first structures were forming from the cosmic fog. Unlike Hubble, which sends back images that resemble photographs, much of Webb's raw data arrives as numbers, intensity values in specific wavelengths that must be processed and translated before they form images. But what emerges is extraordinary. Sharper, deeper views of the universe than we've ever had. Where Hubble showed a mist, Webb reveals a mountain range. Where we once saw outlines, we now see details. Then there is Gaia, a different kind of telescope with a different kind of mission. While Hubble and Webb focus on the depth of the universe, Gaia is mapping its structure, particularly within our own galaxy. Operated by the European Space Agency, Gaia is creating a 3-dimensional map of the Milky Way, charting the positions, motions, distances and brightness of over 1 billion stars. Launched in 2013, Gaia orbits the Sun, not the Earth, in a stable path that allows it to scan the sky continuously. Its precision is staggering. It can measure the thickness of a human hair from 1,000 kilometers away. With that level of detail, it tracks how stars drift through space, how they form clusters, and how our galaxy rotates and evolves. Through Gaia's eyes, we begin to see the Milky Way not as a static disk, but as a living system, dynamic, swirling, full of motion and change. Together, these 3 telescopes give us a kind of binocular vision across time and space. Hubble gives us beauty and structure in visible light. Webb peers deeper and redder, revealing what was once obscured. Gaia maps the stars around us, showing how they move, how they gather, how they trace the skeleton of the galaxy. Each telescope required years of design, international collaboration, and engineering miracles. Webb, for instance, had to be folded like an origami flower to fit inside its launch rocket, then carefully unfolded in space. A process so delicate and complex that it took nearly a month just to deploy its mirrors and sunshield. Hubble, famously, had a flaw in its primary mirror at launch and had to be repaired in orbit by astronauts, a moment of both failure and triumph that ultimately made its mission stronger. These telescopes do not simply show us what is out there. They reveal what is possible, in the cosmos, yes, but also in ourselves. They're reminders that science is not just equations and experiments. It is vision. It is the decision to look deeper, to build better tools, to reach beyond what we can currently see. And through these tools, we're no longer just observers. We are participants in a shared act of discovery. Think of the photons captured by Webb. Some of them launched on their journey over 13 billion years ago, when the universe was still a toddler. They travelled undisturbed across time and space, through the birth and death of stars, through the formation of galaxies, through eras we will never fully grasp. And then, one day, they met a mirror crafted by human hands, a mirror we designed, built, launched, and aligned to receive them. There is something humbling and something quietly miraculous about that. When you see an image from deep space, a nebula blooming in shades of crimson and violet, a galaxy wheeling through shadow and light, or a star cluster glowing like spilled jewels across velvet, it's easy to forget what you're actually looking at. You're not just seeing a photograph, you're seeing the end result of a long, careful translation, a transformation of raw numbers, photons, pixels, and filters into something the human eye and heart can understand. You're seeing data turned into awe. Telescopes like Hubble and Webb do not take pictures in the way a camera does. They don't snap a single image in full colour. Instead, they collect light, often in specific wavelengths, through different filters. Each filter allows only a narrow slice of light to pass through, maybe light emitted by ionized oxygen or glowing hydrogen, or warm dust in the infrared. The detectors then count photons, how many arrive, how bright they are, where they land. What's captured is a grayscale image, light and dark, but no colour. What we think of as a picture is still many steps away. To build the kind of images that fill our screens and imaginations, astronomers combine these grayscale layers. One filter might be assigned red, another green, another blue. Sometimes more filters are used, beyond what a standard camera can see, each one layered and weighted to reveal different structures or elements. The result is often called a composite image. It is not fake, it is a map of light, coloured to convey meaning, not just appearance. There is often artistry in the choices, which filters to highlight, how to balance contrast, whether to centre on a dramatic swirl or a quieter corner. Even the orientation matters. In space, there is no up or down. Every frame is framed by human intent. This is not deception, it's interpretation. The goal is not to make the universe look like something it's not, but to let us perceive what would, otherwise be hidden, to turn the unfamiliar into something graspable, even beautiful. This is why you might see the same object imaged by two different telescopes, and it looks completely different. One might show a nebula as soft blue and white, while another reveals it in reds and golds. The difference isn't contradiction, it's perspective. One telescope might be showing visible light, another infrared. One might highlight glowing gas, another the scattering of starlight on dust. Each is a layer of truth, not the whole truth alone. Some of the most well-known images from Hubble were created this way. The Pillars of Creation, for example, a towering structure of gas and dust in the Eagle Nebula, was assembled using filters that capture ionized oxygen mapped to blue, hydrogen mapped to green, and sulfur mapped to red. This palette, known as the Hubble palette, became iconic not because it was real in the way we perceive colour, but because it revealed structure. The colours distinguish different elements, different temperatures, different layers of cosmic history. With the James Webb Space Telescope, the story continues, only now the light is even older, even fainter, even further into the infrared. Webb's images are often composed of data gathered over hours or even days, filtered and refined by scientists and visualizers working in tandem. Some of Webb's earliest releases, like its view of the Carina Nebula or the Stephens Quintet, were assembled from multiple instruments, across multiple wavelength bands. They are stunning. But more than that, they are informative. They reveal structures within dust, galaxies behind galaxies, arcs of light bent by gravity, textures we've never seen before. And then, after the science is done, after the calibrations and subtractions, the removal of noise, the careful alignment of frames, comes the moment of quiet transformation. When the data is given colour, when the shapes emerge, when the universe begins to take form on a human scale. This is not just technical work, it is an act of visual storytelling. It asks, what is the most honest way to show this? What will help others see what we see? It is also, in many ways, a meditation on truth, because space is not coloured, not in the way we think of colour. There is no sky blue nebula or emerald galaxy floating in the dark. Most stars shine white. Most gas clouds glow faintly, if at all. The colours we assign are at their core symbolic. They represent temperature, composition, motion, distance. They help distinguish features that would otherwise blur together. They are the bridge between what is out there and what we can comprehend. Think of it like music. A single note is a vibration. A pattern of notes becomes melody. A chord becomes harmony. But what we experience as a song is not just sound. It is arrangement, tempo, emphasis, pause. It is interpretation. Cosmic images are much the same. A raw photon count becomes a structure becomes a frame becomes a story. And for those who process these images, scientists, engineers, artists, the task is often one of patience and care, to honour the data, to avoid misleading, to illuminate without distorting. And yet, within that precision, there is room for wonder. There is always wonder. So the next time you see an image from a space telescope, colourful, vast, delicately constructed, pause for a moment. Consider what it took to create it. Not just the machinery in orbit or the code that sifted photons from noise, but the quiet decision to make it visible, to assign meaning, to bring it into view. These images are not photographs in the ordinary sense. They're acts of translation, turning silence into colour, numbers into form, light into feeling. And through them, we are not just spectators of the cosmos, we are its interpreters. If telescopes are our eyes in the dark, then surveys are our memory. They are how we stitch together fleeting glances into a full view, how we gather the scattered pieces of light across time and space and begin to trace the grand patterns of cosmic history. A single image, no matter how sharp, is only one frame in a vast reel. But through surveys we gather many frames, And with enough of them, we begin to see how the universe has changed, how galaxies have grown, and how the story of stars is not a still life, but a film. Among the most ambitious of these cosmic films is the CANDLE Survey, the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey. Conducted with the Hubble Space Telescope, CANDLES was not about looking at one object in exquisite detail. It was about collecting many galaxies at many stages of their lives, across many regions of the sky. Over the course of 900 two-Hubble orbits, the survey captured deep, near-infrared images of 5 different fields, chosen to represent diverse regions of the universe. Its aim: to map the formation and evolution of galaxies over more than 13 billion years of cosmic time. That's not just a number. 13 billion years is nearly the entire history of the universe. Through CANDLES, astronomers gathered light from over 250,000 galaxies, each one a frozen moment in its own evolution. Some are chaotic and lopsided, others smooth and mature. Some are small and bursting with star formation, others are red, massive and silent, retired giants of a younger cosmos. By analysing their shapes, sizes, colours and redshifts, researchers began to build a picture of how galaxies grow, through mergers, through starbursts, through slow accumulation of gas and dust. And because CANDLES focused on the infrared, it could peer back farther than earlier surveys. Young galaxies still full of dust and hidden light became visible. Their glow, redshifted by the expansion of the universe, fell into the exact wavelengths Hubble was equipped to catch. Each exposure was a time capsule. Together they became a time-lapse. Through these frames, the silent metamorphosis of the cosmos unfolded. Yet even the most detailed surveys are by nature fragmented. They are slices of sky, pieces of puzzle. To understand the whole, we need a way to connect those pieces, visually, narratively, spatially. This is where new tools like Galaxy Traverse come in. Galaxy Traverse is a project that transforms raw survey data into something navigable. Using real data from telescopes like Hubble and surveys like CANDLES, it builds immersive visualizations, fly-throughs of the cosmic web, 3D views of galactic structures, cinematic journeys from one galaxy to another. It is science, but it is also storytelling. It turns numbers into motion, maps into voyages. The beauty of Galaxy Traverse lies not just in its visual appeal, but in its accessibility. It makes data that once lived in spreadsheets and scientific journals available as experience, as something you can see, enter, move through. You might begin on the edge of a galactic cluster, then sweep inward past interacting spirals, their arms stretched by gravity. You might fly over a filament of dark matter, traced by the galaxies clinging to its threads. You might pause at a deep field view, the screen filled with ancient light, and know that what you're seeing is not a guess, but a rendering of actual observations. This visual science bridges the gap between information and intuition. It allows us to grasp the structure of the universe not just intellectually, but emotionally. It is one thing to understand that galaxies form filaments and voids. It is another to fly through those filaments, to feel the emptiness open around you, to sense the gravity that binds each dot of light. It turns comprehension into presence, and in doing so, it invites more people into the process of discovery. Astronomical surveys are vast, often too vast for any one team to interpret fully. By visualizing them, by making them interactive and open, we turn passive observation into active exploration. Students, artists, scientists and dreamers can all trace the same paths, can all ask questions, can all see. Behind every survey, of course, is human effort. Years of planning, calibration, observation and analysis. Each field imaged by CANDLES required careful coordination between space telescopes, ground-based observatories and supercomputers. Each data point in Galaxy Traverse was validated, catalogued, transformed, These are not renderings of fiction, but reconstructions of reality. And like all great collaborations, they are greater than the sum of their parts. They are also ongoing. As new telescopes launch, as new surveys begin, the story expands. Missions like Euclid, Roman Space Telescope, and LSST, Legacy Survey of Space and Time, will soon flood our archives with even deeper, wider views. Galaxy catalogues will swell from millions to billions. The cosmic web will come into sharper focus, and the tools to explore it will become richer, more immersive, more human. Because that, in the end, is what these surveys are for. Not just to gather data, but to build connection, to let us see that we are part of something enormous and unfolding. That the galaxy is not distant, they are present. That the story they tell is not closed, it is still being written, one image at a time. And that to trace their paths, even from this small world, is to trace the shape of the universe itself. Sometimes, to understand something truly, you have to take a step back. You have to look from a distance, not to diminish its meaning, but to see it whole. This is especially true for Earth. Up close, our world is filled with detail. Clouds drifting across the sky, oceans shifting with the tides, the rustle of leaves, the hum of cities. But from far away, all of that complexity vanishes into simplicity. Earth becomes not a collection of places, but a single place. Not a story of divisions, but of unity. In 1990, the Voyager 1 spacecraft, already more than 6 billion kilometers from home, was instructed to turn its camera back toward Earth. What it captured would become one of the most famous images ever taken. A tiny dot, less than a pixel wide, floating in a shaft of scattered sunlight. This was the pale blue dot, our planet, as seen from the edge of the solar system. No continents were visible, no signs of civilization, just a speck suspended in the darkness. It was the astronomer Carl Sagan who gave the image its name, and who reminded us of its meaning. "Everyone you love," he wrote, "everyone you ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam." The image did not make Earth seem small in a dismissive way. It made it precious. It reminded us that we are rare and together and fragile. But this wasn't the first time Earth had been seen from beyond. More than 2 decades earlier, during the Apollo 8 mission, astronauts orbiting the Moon looked back and saw Earth rise over the lunar horizon, a blue and white orb suspended in black. That image, known as Earthrise, was spontaneous, unscripted, and quietly revolutionary. Until that moment, no human had seen our planet as a whole. We had maps, we had globes, but we had never seen Earth as it is, a shimmering bounded sphere without borders, without context, afloat in silence. From that vantage point, political boundaries disappear. The things we argue over, land, lines, flags, fade into irrelevance. What remains is the wholeness of the world, its fragility, its beauty, its aloneness. The moon beneath the astronauts was grey and lifeless. The sky around them was empty. But Earth was alive. You could see it. You could feel it. Today we have newer images, clearer ones, high-definition photographs taken by satellites like rediscover, which shows Earth as a constantly turning globe, sunlight shifting across continents. Images from weather satellites that let us watch storms bloom and dissolve, clouds curling and reforming. But none of them quite carry the same emotional gravity as those first views from afar. Perhaps it is because we're used to them now, or perhaps it is because the shock of perspective, the realization that this is it, this is all, can only hit so many times before it becomes part of us. And yet, every time we look again, we are reminded Earth is finite. It is not endless. Its atmosphere is thin. Its ecosystems are intricate. its balance is delicate. The blue oceans and green forests and swirling white clouds, these are not common. They are, as far as we know, unique. Nowhere else, among the thousands of exoplanets we've discovered, have we yet found a world so comfortably suited to life. Nowhere else has given us the warmth of sun on skin, the taste of water, the breath of air. From space, Earth glows. Not with heat or fire, but with life. It is radiant in a way that speaks not only to its physical properties, but to its role as home. It is a sanctuary in the dark, a cradle suspended between stars. And as we study the cosmos, as we chart distant galaxies and dream of interstellar voyages, we're also reminded over and over that what we have here is extraordinary. These images, these distant gazes, are not just beautiful, they're clarifying. They help us see the truth of our condition, that we share a single atmosphere, that our fates are linked, that climate and ecology, politics and economy all converge on this one small marble, that we are passengers together, floating through space on a ship with no backup, no spare. And perhaps that is why so many astronauts, after seeing Earth from space, speak of what they call the overview effect, a shift in awareness, a deep emotional response to the sight of Earth as a single, borderless entity. Some describe it as a feeling of unity, others as grief. But all speak of a newfound urgency to protect this place, not because it is ours to own, but because it is ours to care for. We often think of exploration as a journey outward, into space, into the unknown. But sometimes the most profound revelations come when we look back, when we see what we already have, as if for the first time. Earth is not just a place, it is a perspective, a point of origin, a question mark, a refuge. It is where the story began, and where for now it continues. And from 1 billion miles away it is only a dot, but what a dot it is. And now, at the end of this long, quiet voyage, across planets and nebulae, star clusters and galaxies, through light and distance and time, we find ourselves back where we began, on Earth, still spinning, still breathing, still wondering. Perhaps the most astonishing truth of all, after everything we've seen, is this: we belong here, and at the same time we belong to the stars. It's not just poetry, it's not just a metaphor whispered at the end of a stargazing night. It is science, it is biology, it is chemistry. The atoms in your body, your carbon, your nitrogen, your iron, were not formed on Earth. They were born in the cores of stars billions of years ago, in nuclear furnaces so hot and dense they could overcome the forces that keep atomic nuclei apart. And when those stars reached the end of their lives, when they exploded in supernovae, they scattered those elements outward, into clouds, into dust, into future planets, into future people. You're not simply on a planet that orbits a star. You are the result of stars. You're stardust that learned to walk, to speak, to listen. Stardust that became conscious of itself, a way for the universe to know it exists. A temporary arrangement of particles with the extraordinary privilege of wondering where it came from. And yet, for all our origins in fire and fusion, we find meaning in stillness, in quiet, in the pause between questions. That's part of the paradox, isn't it? That the universe is vast and expanding, full of light and force, yet what we long for, what we cherish, are the calm moments, the hush of a forest, the warmth of another person's voice, the comfort of rest. We are forged from stars, but we're nourished by tenderness. There's a quiet comfort in knowing that we are small, not insignificant, never that, but small in the sense that we're not alone in carrying the weight of existence. The stars do that too, the galaxies do. The cosmos holds its own story, and we are part of its telling, but not its centre. And somehow, that makes our place more beautiful. We do not need to be the reason for the universe to find purpose within it. Even in the deeper silence, there is connection. Light that left a galaxy 10 billion years ago now meets your eyes. Particles that formed in a long-dead star now flow through your bloodstream. The breath you take tonight contains atoms that once belonged to mountains, to oceans, to strangers. We're not isolated. We're entangled. In time, in matter, in memory. This idea that we are linked to the universe not just by space but by substance can be a gentle companion in the dark. When the night feels too vast, when the stars feel too distant, remember that you are made of the same light that shines above you. The same processes that built nebulae built you. The same elements that power suns now fuel your cells. The same gravity that sculpts galaxies holds you to the ground. The universe is not somewhere else. It is here, unfolding through you, around you, within you. And so, after tracing the farthest reaches of what we can see, after mapping the cold brilliance of galaxies and the glowing clouds of stellar nurseries, we return, not just to Earth, but to the quiet space inside ourselves, that place where wonder lives, that place where rest can begin, because the stars are still there, the universe is still expanding, the galaxies still drift, and new stars are being born, and old ones are fading. But you can rest now. You can let those thoughts float for a while, like leaves on a gentle stream. Let them drift out into the dark, where they can settle, or disappear, or return to you in dreams. There is no need to hold on tightly to every fact. You've seen enough for now, you've walked far enough for tonight. The cosmos will keep turning, the light will keep coming, and you will be here, on this pale blue dot, carried safely in the arms of the same stars that once gave you form. So breathe in, let the quiet deepen, and sleep, dear traveller. You're very old, and just beginning.